So welcome to this afternoon's lecture to be given by Professor Kallio. And he is a professor at the University of Aalto in Finland, and he's in the department called Department of Electronics and Nano Engineering. And he's very young. He got his PhD in 1996 from Helsinki. And then he went to UC Berkeley for postdoc, and then he went on and the first time I heard of his name, read about him, is when he was working at the Finnish Meteorological Institute. So he worked there for, I think, for 10 years, something like that, and then he moved to the university and to start his education career to some extent, and then he also starting his work on cubesat. That's very interesting. I think his group is very interesting group that produced some very outstanding scientists and engineers. I try to just before I try to download his CV and Tensor, I got about 20 pages, of print out. And we have invited Isa to give talks before. I think it must be about 2 years ago, right? 1 and 2 years ago. But now he is going to tell us about his very successful project called Suomi 100 CubeSat project. In terms of his institute, is doing very well. His group is doing very well. And even maybe later on, if he had time, he would talk about the ICE-I, right? ICE-I project, which I think he told me once that he was just some colleagues next door to him lab working on that project. Now it's become a very, very interesting and important project for nano satellite with SAR. And I think that so there's something that we should learn from them. Isa, so now it's all yours the time. Please go ahead.
Thank you very much. Thank you for the very kind introduction, and thank you for the possibility to give this seminar. And I apologize because I had some problems with the camera. The system doesn't let me use the camera, but you don't lose much. I think that slides are more important than my face. Yes, actually, as Professor Ip just mentioned, so I've been working quite a lot with the Finnish Meteorological Institute, and I worked there in several ESA, European Space Agency space missions, and I'm still working. But those missions, for example, I'm involved in JUICE mission. It will be launched in 2 months from now. And Baby Colombo is approaching Mercury. Those are so roughly about 20 years project. So maybe it takes 20 years when you start the project, when you get the data. And at least at my age, 20 years is quite a long time. So that's maybe one motivation why I'm in recent years being more very interested also possibilities to use small satellites, especially this kind of CubeSats, where we can build it fast and where we get data fast. And in addition to this kind of scientific quick data return, this also on educational point of view very motivating, because the same students who are involved in the project to develop the satellite or instruments, they can actually also even analyze the data when they are still studying at the university. So there are several, at least those 2 reasons what I'm motivated. Yes, unfortunately I don't have a camera here. I could have shown a real size model of our CubeSat. So it's a smallest CubeSat standard. It's a so-called 1 unit, a volume 1 liter, dimension 10 centimeter, 10 centimeter, and 10 centimeter to third dimensions. And I will focus on science because I'm a space physicist. I will tell about some lessons. Actually, those lessons are especially concerning how we can optimize our science return from small satellites when we have many this kind of challenges and problems what we don't have if we have a very large, well-tested, well-controlled spacecraft. But there are certain very important benefits when we have a small satellites. Maybe already now I could mention that, for example, when we own the satellites and we own the instruments, so we can use those instruments whenever we want, in a way what we want. If we have a large satellites, you could have over 10 instruments. You have to make a lot of planning and design when you can use your instrument, how much you can get data, sharing of the telemetry, lot of negotiations, and you cannot control the satellite, you can control your instruments. But here we have a more free hands. And actually, I will tell about the camera. You can actually, we have two payloads. One is the camera. Already here you can see the camera lens. And here, this is the photograph taking when the satellite still was in our laboratory. But this is a real photograph. I will show, this is a part of the small, larger photograph. But it really tells that also our camera is working. But okay, I will come back to those a little bit later. So I will start to tell about why we built this Suomi 100. So 100 in Finland, when you pronounce it, it's a sata. So it might be that many times, please don't be surprised if I said Suomi sata. I mean, Suomi, it means saying that Suomi 100. So I tell about the background, now focusing on the science background and the research goals. So I say that when I refer, I will refer that it's an auroral satellite. And the reason is that we have a camera. And this is this kind of summary of two events that I will now introduce. One event is from our auroral observations. So, okay, Finland, I'm somewhere here, the northern of Finland is here. And now when we took a camera, when our satellite was here, we looked to this direction, to Finland, Norway, and we see, so this kind of image of aurora. I will show larger images later. And the second example is that we have a radio instrument to observe radio waves in megahertz range. We make an observation when we moved above ice cut transmitter, radar transmitter, and we observed radio waves when we were close to that radar. So I will show and I will tell about this event, and also what kind of difficulties, problems we had to analyze camera observations and radio observations, and actually what kind of lessons we have learned so far. So far means that we have been in space 4 years and 2 months. I will also come back to that one. As I mentioned, we have a camera and a radio instrument. Radio spectrometer means that we can sweep different frequencies, not only use some constant frequency. And about also what lessons, already maybe I say that when we have a simple instruments, you have to be prepared to spend a lot of time to make a data analysis. Because then you have to on ground compensate the limitations and what you have made when you developed your space instrument. Because you can imagine that even if the whole satellite is a 1 liter, the volume is 1 liter, the instruments have to be very simple, and you have to include more data, so let's say simulations and these kind of things to really use the data effectively. But I also come back to that one. So the lessons. Okay, I look how much time I have. Yes, the lessons, especially on focusing on the research and how to use instrument and the data. Calibration, instrument calibration, some remark about ground stations. Of course, when I say that how to reach scientific goals, of course, then the technology have to be working. For example, the reason why I bring up ground station is that, of course, you have to give commands to satellite and you have to get the data down. Maybe you already know we have our own ground stations, but nowadays, if you want, you can buy ground station time from commercial companies. So, okay, but I will come back to that one. But it might be that you don't have this kind of ground station problems. For example, what we have had if you buy it from some companies. But for example, we wanted to make our own ground stations because we are university and really wanted to students can teach, students can learn how to build ground station, what kind of difficulties there are, and also how to control and use ground station. Observations, because the satellite typically have a quite short lifetime, especially when we have small satellites, cubesats, because they are commercial components, and very often those who build are not this kind of experts who have developed instruments 20 or 30 years, for example, my colleagues at the Finnish Meteorological Institute, but they are students who have some experience of electronics and softwares, but they have at the same time courses what they have to take care of, and students have only limited amount of time. So also this really makes some challenges to make long living small satellites at the university level. Okay, then as I mentioned that you have to spend a lot of time to interpret the data. For example, I'm now interpreting observations that we take over 4 years ago, and now I'm accomplishing the JGR revised version where we have analyzed in some detail this image. I will come back what kind of difficulties we have had. And of course, we want to optimize. This is a very small amount of data, but you can get small satellites. So of course, one lesson maybe only now is that it's good idea to make a joint observation and try to combine your space observations as much to ground-based observations as possible. And I will come back to that one, this joint observation. One example is this ice cut heater and our CubeSat observations that I mentioned. So I think that I mentioned quite many things that I can speed up when we have those slides available. A reminder that it was a joint combination to the Finnish Meteorological Institute. Actually, I worked 25 years at the Finnish Meteorological Institute before I came to Aalto University. And this is joint project together with Aalto and Finnish Meteorological Institute. We lead the project, and Finnish Meteorological Institute was a co-principal investigator institute, and actually they made the software because one of their expertise is on-board software, and we get funding thanks to all funding sources from the government, institutes, companies, universities. Maybe I go this quickly. If you are a little bit interested about this project, we have a web page. Unfortunately, most of our information is written in Finnish, and now our idea is that we also start to translate that in English, but there is at the moment only one English page. And actually, the reason why we have a Finnish page is that we celebrated when Finland have a 100 Independence year, 2017 December. So that's the reason why there is the name 100, so 100, and the Suomi means Finland in Finnish language. Okay, it was a third Aalto University's cubesat. So there is my students who make a vibration test of the radio instrument 3D printed part, our electronic laboratory where they make some kind of some testing, and also in our electronic laboratory we have a clean room, and actually this is the real live model of this Suomi satellite. As I mentioned, we have been in space 4 years. SpaceX Falcon 9 from Vandenberg from California. Falcon 9 here, actually this was used already once or maybe 2 times before, because this is they can reuse part of this launcher. And it was the polar orbit, about 600 kilometers altitude, maybe now it's about 580 approximately. And here you can see the ground track of the spacecraft during one day. And one lesson what you can here learn, that actually if you could collect the data during the one day, you could get data from very many latitude and longitude points. Okay, what is the maximum latitude and latitude in north and south? It depends on the time, and for example, in this time we could not see almost. Okay, there is about 10 degree hole here, and every day those ground tracks moves a little bit. So let's say during 1 month you can get a very nice coverage if you want to take images, or if you want to take some specific observations. For example, we investigated the ice cut heater is here. For example, this track is not very ideal to make a heater, but actually we decided to wait such a time that the spacecraft moved close to ice cut heater, that I will come back to that one a little bit later. As if we take two solar panels away, we could see inside, so there is a camera board. This is our electronic board, and the radio instrument was or actually it's our main scientific instrument, and it is house made. Students really designed and built, tested, and actually used, and knock the wood, it's still working very well. Okay, then you have to have a platform. Okay, then there's a camera, as I mentioned about, it's a polar orbit about 600 kilometers, mass about a little bit more than 1 kilogram, and the size I already mentioned. And already, as I mentioned, so I'm a space physicist, and I'm interested about the space weather, or actually in general how the sun affects different solar system planets and objects like asteroids and moons. And with its solar wind, so charged particles, and with its photons, so sunlight that make an ionosphere. And actually, we have a lot of ground-based instrumentation especially in Scandinavia, in our rural region, and I will discuss more about this ice cut. It is in Norway. Actually, here you can see VHF and UHF antennas, and actually you cannot see here, but on ground there are antennas on ground, and I have another picture what we used in joint observations. If you are interested, you can, unfortunately, you maybe cannot see this link very carefully. We have to make a virtual reality software where we have included our simulations of the Sun, Mercury, Venus, Earth, Mars, a comet Churyumov-Gerasimenko, and actually you can go in this our solar system, simulated solar system, and now we also have a Windows version if you don't have a virtual reality glasses. Maybe can I start? Okay, maybe I skip that one, but I can tell more about later if you want to know more about this one, but let's focus on science. So first 4 years in space. So first about the camera instrument. Some technical details. So this is really commercial, normal white light camera. White light camera means that when we took photographs on ground, they looks, you can see the red, green, blue, similar as in normal cameras. For 3 megapixel camera, we wanted to take an image of auroras, and then at least my opinion is, before we launched, and my opinion still is, that it's good to have a wide angle camera. It can increase your possibility that you can capture auroras in the field of view. And one reason why it can be complicated is attitude control problems. It's a very typical that you cannot in detail control what is the direction of your spacecraft. So what is the orientation of your camera? So what is your looking direction? So therefore it's good to have a large field of view. So it creates the probability that when the satellite is rotating, wobbling, so you can still maybe get an auroras, see auroras. So we had about 45 field of view degrees in diagonal degree. So quite a small ground pixel size. Okay, technical details. We have published one paper of camera that we use those. I can give references, and I think that I have those references also at the end of this presentation and in some of those plots. Maybe already now, one thing that I will also come back later, one lesson, and it is associated to the fact that you have to be prepared that your spacecraft is alive only maybe 1 day, 1 week, 1 week, 1 month. It can be several months. For example, our satellite is still healthy after 4 years. So our strategy is that, okay, camera instrument is that in that respect important for outreach activities. We, for example, wanted to immediately see the communities and the Finnish people, citizens, and to all over the world that our satellite is working. And if you take an images, you don't have to be expert to really see that yes, you are in space and you have getting nice data. And first, our approach is to use camera and the first day side images. And here you can see example of our day side images on clouds almost 2 weeks after the launch. This is okay, almost immediately after the launch, 1 week after the launch. And when you look this image, you can actually see that it's this kind of image that is a combination of 3 images. You cannot see here the boundaries because the software combines so nicely, but you can use your imagination that there's 1 image here, 1 image here, and the third image is somewhere here. And the reason why you can get this kind of is that the satellite is a little bit rotating. As I mentioned, it's a problem if you really want to look exactly to one direction. But you can use it. There are some good features if you, for example, take several images, 1 image and 1 image, second image, third image. You take a sequence of images in such a way that those in part of those image field of view are the same. Then you can combine and get to this kind of larger field of view. This is larger region. This is 3 photographs. Here is 2 photographs. These outer Hebrides are actually north of Scotland. Here, this is a combination of 5 photographs, and actually the 5 photographs, it's not so beautiful that there's 1 photograph, 2 photographs. Actually, there is a lot of photograph information around, but then I wanted to cut very nice this kind of piece of data. So can actually, there's a limb of the earth, and okay, there's also night side. You can see almost the whole field of view of the camera, what camera can see in this direction, from this direction. And to us, it told that, okay, maybe camera is still working. But after that one, when we knew a little bit how to use the camera, and it works on the day side, because it's much more easier to take day side images than a night side images. Because of you have to have a longer exposure time to get enough lights. And okay, we didn't exactly know, can we see auroras? So can we use such exposure time that we can really see auroras? And luckily, it turns out that when we use certain, in our case, it was about 2 seconds, we can see auroras. And actually, you can see a little bit green auroras closer to Earth, and red auroras a little bit above the Earth. And I want to show and point out 2 actually lessons from this image. As I mentioned, we cannot control our attitude. We want to always control that it's not rotating very fast. As I mentioned, sometimes it's good that it's rotating, but we don't know exactly what is our direction, but we can use stars to get information that to which direction we are looking. And for example, here, actually this aurora is almost the background. You can see Aguilas constellation, and it gives us information that, okay, now we know the attitude. One lesson more, we don't have a GPS, so we don't exactly know where we are. So we also, this is something that we have to calculate it from orbital parameters. It would be nice to have it from GPS, but we didn't have time to include GPS. And another lesson is that, as you can see, I say that it's the spacecraft is rotating, but in order that we can capture auroras, we have to use quite large, about 2 seconds exposure time. So therefore, for example, you can see that during that those light sources on the surface, they make this kind of circle. So you can imagine that the satellite is rotation axis is maybe somewhere here. But it also means that this aurora becomes a little bit blur. And of course, it's a scientific point of view. This is not nice. It would be nice to have a very small exposure time, let's say much less than a second, to really see in more detail the auroras. But this is only what we can get with the small satellites. So you have to use some extra information to really use this data. Camera observations, as our intention was not to take image of the moon, and our moon is actually very small. Actually, this is also a zoom of the large image. But anyway, we can get some pixels, and one lesson is the calibration. And only now you can see that we can use moon to calibrate our camera instrument. And actually, we can also use stars to calibrate our instrumentation. I will come back to calibration a little bit, maybe already now. So we have, this is the image of a couple of stars, and okay, they are not very clear, but anyway, you can get red, green, and blue channel values from those, and you can also by visual inspection see that, okay, red, green, and blue colors are different. So actually, we made a star model because we have a certain information from different space missions about what is the spectral shape of stars. so we could make a model of the moon and stars, and in such a way we could recalibrate and also make that calibration in space. And actually this is Olli Knuttila's paper, actually Olli visited also at your university several years ago. So he had worked with the cameras. But as I said, our main scientific instrument is radio spectrometer, and okay, we use this kind of commercial components. We could say that this is some kind of old radio car radio instrument. Sorry, old car radio in the space. Car radio AM that observe AM amplitude modified signals. And actually this chip was really for this kind of radio instruments, but now we use it to make a science. Frequency range from about 5 to 10 megahertz, it's the most sensitive. Okay, as I mentioned, we built it in house. And this gives one important example. And actually this is what we did in ice cut radar. So in this drawing, you can see altitude. We are at altitude about 600 kilometers. And actually here you can see the distance from some kind of source. In here we have a source, it's a radar. And in this frequency range, let's say 5 to megahertz range, ionosphere, so charged particles, in this case, they are electrons that are affecting to the propagation of radio waves. So radio waves, they don't propagate like a straight line, but ionosphere, electrons are affecting. So the path is a little bit disturbed. It's not like a light, like a straight line. Some of those can even bounce back to ground. And our scientific goal is that, okay, we are moving close to the transmitter and we are listening the same frequency, in our case about 8 megahertz frequency. That is transmitted, and we look when we hear how strong the signal is and maybe how disturbed it is when we move near the transmitter. And these active measurements I will mention. Okay, I already mentioned briefly, but maybe I just mentioned briefly more again, calibration. So actually when you decide an instrument, also especially a small instrument, so it's good to spend as much time to make a calibration as possible. Of course, first in the ground. We use in the camera calibration our monochromator. It sends a very narrow wavelength in a one-dead frequency, and we use red and green wavelengths because they are the most intense emission from the auroras. And at the same time, we could see that if we have a very little light, what kind of artifacts the camera sensor and the data compression JPEG cause, so that we really could be prepared that, okay, we should clean the data, and it's quite easy to clean because those stripes are very clear. And then we could also see that actually what is the intensity of red and green lights. We really knew exactly what is the intensity of this monochromator. And then, as I mentioned, we also made in space by using not man-made emission source, but natural emission sources. We also make some calibration, but unfortunately we didn't have time enough to make a really detailed, to calibrate our radio spectrometer in ground. And we have in-house made so-called G10 gigahertz transfer electromagnetic device. There is a door. We could include our cubesat, 1 unit cubesat, or our radio instruments. There is a transmitter here, and then it transmitted the wave that is quite a plain wave at this point. So we could really see that what is the response, how strong signal we get when we transmit different megahertz signals from here, where the transmitter, our receiver here. But as I said, we didn't have enough time to do it very carefully. But luckily we can use also this radar signal to make calibration. So when we are flying above the ice cut heater, it's over here. I will come back to one. We know exactly what is the transmitter power. But then we have a model how ionosphere is affecting, so we can make in space calibration, absolute calibration of our radio instrument. Just briefly, ground station, as I already mentioned, it can be very problematic. There can be hardware problems. For example, there is a rotator that is rotating these Yagi antennas because we want to follow the antennas. It can be that your rotator doesn't follow the satellite very carefully. Some electronic problems, it might be that the cables get water. It might be that you have some software problems. Even if you have one satellite, it might be that there are some software updates what you have to make, especially when if you have several satellites and you have different requirements and needs for the satellites. It might be that the changing of some part of the software to some applications is affect to another satellites. So at least I wasn't aware about how challenging this kind of satellite operation is. And once again, because operators are students. For example, this is my student who is now working at the Finnish Meteorological Institute. So students also have some other commitments. So when there is a problem, this kind of students are not immediately possible. So typically we will lose data because, for example, we cannot send commands. We don't get down to data. And as I already mentioned, it's good to already be prepared that you have limited amount of lifetime. So that it's good that make the plan that, let's say, during the first month you can get at least something. And we started with the camera, as I mentioned. First, take as much day-side photographs as possible, as much night-side photograph as possible. We were lucky that we actually get auroral images at this stage. But then our main instruments is this radio, and then we started almost immediately. Maybe we used that only 1 month or so. Start to collect observations by certain frequency. We have different data modes, high data modes to make very detailed observations, and average modes to make global observations. And then we just similarly as cameras, we just wanted to get as much data as possible. Then we started to focus on, okay, what is the most useful data? And also then we also had an idea to make a joint observations, and we already have made 2 observations with the ice cut heater. I will come back to that. Then, as I mentioned, the interpretation of the data, it takes a lot of time. This is this event, this auroral event. You can see here one part. As I mentioned, we have to use orbital parameters. In our case, it is enough because we also have other uncertainties. As I mentioned, the satellite is rotating, so we don't get a very clear snapshots. But here you can see, okay, already here image, you can see some auroras, but it's not so very clear. Here, the spacecraft is now rotated. You can see that this image is not like this one. This is, I would say, the most beautiful one because auroras is almost at the center of the image, and the limb is also very nice. Here actually there's a one rotation, so in this rotation aurora was here. After one rotation it was here, and this was I think more clearer than this one. And if we put that in the map, actually the look direction is somewhere like here. Longyearbyen, Norway is here. Tromsø, ice cap heater, is here. And here you can see part of the Finland, northern Finland is here. And aurora somewhere between. And actually you can see also one star over here. And okay, my plan is to send on Friday the revised version of this paper. Already now you can see the original version, but the new version is much more better. If you are interested, I can send that version to you at the same time when I send it to JGR. So how to use that data? Here you can see, as I said, we have a red, green, blue camera. We have a red channel, green channel, and blue channel. And here you can see that in the red channel and green channel you can see the most cleanest clear signal, and it's something from the theory is expected. The blue is not so clear as it should be. So how to interpret the data? We make a 3D auroral emission model where we can manually put emission model for red, green, and blue lights. For example, here you can see red, green, and blue emission where we use Chapman emission profiles. Here the emission is everywhere in the ground, everywhere around the Earth, but actually we knew this box actually shows that we actually see auroras in this region. So we know that, okay, in this model we only have to take parts of the emission from this part. And okay, we know that our spacecraft is here. We know the direction, so we can look from where this emission is coming from. We know that, okay, auroras is somewhere in this line of sight, somewhere here. Already now, we also combine it with the ground-based observations. As you might know, we have all sky cameras that always take images of auroras. For example, in Norway, once again in Svalbard, in Finland, in Norway, and those red shows what is the field of view of the cameras at altitude at about 200 kilometers. So actually we can see that we could actually capture this kind of space regions that what we cannot get from auroral images. And actually our simulation shows that if you look carefully, you can see that the green auroral emission maximum is closer to Earth than the red emission. And actually the distance between the red altitude distance, what you can see in this image, it depends on how far the auroral emission is from the camera. And actually it turns out that our auroral emission is somewhere here, according to simulation. So even in one camera, it might be that when you combine it with the simulation, you can get where some localized so-called discrete auroras are. Some problems or challenges to get a radio instrument. I didn't mention that the antennas what we have are very simple ferrite rod antennas. And in ferrite rod antennas, actually it collects signals practically at every direction. Only it cannot collect along the ferrite rod axis. And also we don't know exact attitude of the spacecraft. It means that when we get signal from our radio instrument, we don't know from where it's coming from. So we have to be prepared that, okay, it might be that some of the signals are coming from the ground. And actually here you can see example of our wavelength, what we observe. this is the time, and actually this is the signal observed from the wind waves actually between the moon and the earth. And you can see that, that if you want to observe natural signals, unfortunately you have to be prepared that there are man-made noise that actually goes through the ionosphere. I'm a scientist, so I'm especially interested about natural signals, and there are in this frequency range from 5 to 10 megahertz. You can also observe what is happening on the sun, observe high radio waves caused by high energy electrons from the sun. So you have to be prepared that there is man-made signals and there is also natural signals. So once again, simulations. So for example, here we simulated that, okay, if we have instrument here above, okay, once again, there is Finland, Helsinki is here, and if we, for example, our satellite is above the Helsinki, from where that about, I think that it was about 7 megahertz signals or 8 megahertz signals, where it can come from. And in this ray tracing band, we can see that part of the signals can come from space. You can see how the radio waves can approach the Earth, but because of the ionosphere, they are bouncing back. Or they can go through the ionosphere almost directly. Or they can be man-made signal that is coming from here. Ionosphere is disturbing signals. But we don't know what is the actual direction of the signal. But this anyway helps. If we know that there is some radio source above, this gives us hint that maybe it was some man-made signal. Okay, I mentioned the reason of those one. For example, here we investigated if we have a 7 megahertz signal that is close to this ice cut was 8 megahertz signal. You can see that part of those signals can go through the ionosphere, parts of those are bouncing back. So it means that if we move above some source, let's say about 600 kilometers, in the simulation we can investigate that how strong this signal is on the plane above the signal. And for example, here you can see the signal map. So if you take this map, you calculate the source strength of the signal. Very naturally, the highest signal is above the source, but then there is also some signal, and you can see what is the signal strength. And then you can investigate how your instrument can observe those signals. But as I mentioned, we have this 1000 observations per second high data rate, but then we also have this kind of low data rate, typically 5 observations per second. And one challenge in CubeSats is that when you don't have a good attitude, it's very difficult to get a good downlink data, because if you use high frequencies, you should have a very good pointing accuracy. But we have only these VHF frequencies, so our data rate is very low. So we cannot collect all times high resolution data and get it down. Here we have get data from every 1 second, and actually the color here shows what is the strength of the signal during one orbit. And this is what we are collecting, this kind of radio noise, and interpretation of this data is much more complicated. It's very complicated. But these joint observations, as I mentioned, time is running, I apologize. I will more tell about this event, these joint observations. We have many on ground observations. As I mentioned, we have all sky cameras, we have magnetometers, IceCat, now we are building IceCat 3D, ryometers, ionosones. Tromsø, we have IceCat heater. Here you can see once again photograph of this IceCat. This was this UHF, VHF, but now as I mentioned, there are very large antenna arrays. There are actually three antennas, 1, 2, 3, and they gives sinusoidal frequencies, sinusoidal signal from about 4 megahertz to about 8 megahertz. It's a very localized signal. So actually, this kind of the power compared to this kind of uniform transmitter is very large, corresponding a gigawatt or so. So we are moving here above this one, antenna one, that is here. Over here you can actually see two parts what we investigated. This is published in Radio Science. It's open. You can open it, download it, and we wanted to now make sure that the signal is really from the ice cut heater. There is a time. Here you can see the transmission power. 1 second time, this kind of time pulses, and in these parts we increase 0.2 second, we increase 0.2 second, 0.2 second, 100 maximum power to go to 0. So we made this kind of ramp of the power. So in order that we can really make sure that this signal really is coming from the ice cut heater. And one important thing, we can see what is the response of ionosphere to different power. It's not a linear power, and actually it turns out that we observed something that is expected to be in the theory. So when we pump energy to the ionosphere, it heats electrons, and the transmission of the next signal is different because ionosphere is affecting, and actually we saw this kind of how ionosphere is responding to the heater. But maybe just quickly, as I mentioned, we have all sky cameras. So when we took an image, we also compare it to the all sky cameras. There are different kind of other data, for example, the scanning photometer from Långerbuen, and we also have magnetometers, radiometers, ionosondes. Okay, so let's some concluding remarks. So we have been in space for years and used our instruments, and at least in my mind, and I think that at least there are also some scientists who share my opinion, even this kind of small, even you can use an important new science even with this kind of small satellite and with this kind of very simple instrumentation. For example, auroras. This is this Olli Knuttila's paper, camera paper. Then, as I mentioned, this analysis of auroral images. In ionosphere, as I mentioned, this ice cut heater, and we are now preparing this kind of global measurement observations. And I really hope that we will get more data later, because it might be that we are still in space about 10 years. It's very likely that our instruments are not working 10 years, but hopefully they work as long as possible. So we are collecting data. And okay, some lessons is concerning especially how to make science, how to get a lot of science, maximize the science return, is that spend time to make calibration on ground, and if possible also in space, because you have a simple instruments. A ground station, if you use your own ground station, if you want to get data, spend time to make a reliable ground station and prepare that there are some unexpected problems. Make a plan that you can get hopefully important information even if your lifetime of the spacecraft is 1 week, 1 month or so. When you get the data, there is many limitations associated to the observation and your instrumentation. So please be prepared, try to compensate this quality of the data with the work on ground, modeling, compared with some other observations. And at least one lesson is that at least when you combine your tiny amount of data to a larger amount of data, it really you can optimize the science return of your instrument. So it's work. Please prepared to do that. But of course, this is interesting work, and this is actually the reason why we build the spacecraft and build the instrument. Yes. So thank you for your attention.
Yeah, thank you so much, Kallio. And if anyone interested in because Isa could not have his camera on, so I want to show you his picture. You can see this is the Isa, right? Is that you, right?
Yes, yes. There is
handsome gentleman there. So we are open for questions for this very interesting talk. Even though I have a number of questions to ask, but I think I will let the audience to. You could ask him by open your mic. You could type it in your chat box, because I can. If you could type it in Chinese, I could translate it into English. Now I can see already a number of questions from Professor Gao Shenlong. Professor Gao. Yeah, okay, Professor Gao, can you write it down again, on the chat box so that he could see, because indeed the sound is
okay,
not
sorry.
Okay.
Yeah.
Sorry, my microphone is not very good.
Yeah.
Okay.
When you're writing down the question again, I ask Isa some question. So I mean, I see that you said the camera you use is a commercial one, right?
Yes, it is.
So you just go to some supermarket to get it, or you have some requirement, the test requirement.
So this camera was bought from one space company actually who is building those for space applications.
Okay.
So we already knew that this is it can be true, it can be good, and also because there is a flight heritage, so
Right.
so it was reliable. It wasn't this kind of camera that people are using, taking photographs on ground. So.
Okay, good. So I understand. So I thought that you just go to the supermarket and get it. Well, it's not the case. And on your one your CubeSat has a small antenna. So I would like to know how much time did you need to download one image, the 3 megapixel image.
Yes, this is a good question. And actually, this is associated, as I mentioned, to our low data telemetry, and also the challenges on the ground station. For example, at the beginning, when we start to get data down, one student always send a comments, spend a lot of time by manually getting down data, because it's certain telemetry packages, and we have to have many telemetry packages. For example, now we have never downloaded raw data. So really this raw 3 megapixel data, because it would take so long time. We have only those JPEG compressed images where the size is several hundred kilobits. So getting one real this kind of images, the total images, how much it took? I would say that it takes, let's say, 1 week approximately. Order. So it takes so long time that we have not downloaded maybe 20 JPEG images, because typically we download so-called thumbnails. Thumbnails means that it's a very low resolution photographs, and then we download those thumbnails. If it looks like that this image includes scientifically important, then we download the JPEG image. So this is our strategy.
Okay, and one question that I really am interested in: how much what's the cost? What's the budget for your mission?
Yeah, this is you know, yeah. The good thing is that I can always say that I don't exactly know, and this is the honest answer. Because one thing is that because this is a student university project, so we wanted to optimize student power. So actually, if you would like to make this kind of work by using salary to your group members, it would be so much that we could never have made this kind of. But students get degrees, they get credits, and of course they get an expertise. And thanks to that one, for example, the student what you showed those images, some of those are in this ice icon company, for example, as was mentioned at the beginning. So I know some how much some of those launch, for example, launch was quite expensive, and because we need to launch our satellite as soon as possible, because this was also a government project, and we had to actually, our main plan is that when Finland have this 100 jubilee 2017, we are in space. Actually because of the 1 year delay, launch problems in India, and this we have to transfer our launch to California. So it was 2018, and the launch was almost 70,000 euro. 70,000. Nowadays it's a cheaper. They are the price have going down, and if you don't have so much hurry, if you can spend longer time, the launch cost will be smaller. But so thank you for the question, but unfortunately I don't know exactly.
Yeah, that's good. And then now that you can see the writing of by Professor Go on the chat box, can you see that?
Yes, now I can. Unfortunately, yes, I apologize. I didn't recognize that there is a chat. So what question you would like to answer, to get an answer?
He's interested in observing, in monitoring the ship, the vessel on the ocean. So he would like to know whether the camera can be used at night for vessel monitoring.
Yes, it's I don't believe that on nights, because as the ground pixel size is about 2000 meters. So the pixel size is very large because we want to have a large field of view. So we cannot make this kind of ground monitoring. And this was a decision. We could also have a very narrow band, but I'm sure, sorry, narrow band, small field of view, but I'm sure that we wouldn't have auroral images then. So
Yeah.
I would guess my educated answer is that no.
Maybe yes, because you're talking about aircraft carrier, big ship. Yeah. So there's another question by Zhixiong Lin, right? Can you read that? He says, he asked, how does good images be selected on board for downloading? That's a good question, I think.
How does good images be selected on board for downloading? Yes.
So, are you there?
Yes, I am.
Yeah.
Can you hear? Yes. So as I mentioned, because of the low data telemetry, we first download thumbnails. They are very small, about a kilo size files. We have hundreds of those thumbnails. Then by manual inspection, we choose the best one. But we also have some kind of simple artificial intelligence in that respect, that student, my doctoral student Olli Knuuttila, made several algorithms that automatically identify are there auroras in the image. He used ground images of auroras, green, red channels and really make a software that evaluates that are there auroras into image. But we have not used that one. So far we have only used by visual inspection.
Okay, I think that if you want to ask Isa more, you could write to him.
Yes, please.
If you don't have his email address, then write to me. I can send you his email address. Now there's another question by York Lin. Can you read that, Isa?
Yes, since cubesat engineering as under participant, the question might appear. Okay, okay, how you made purchase and development decisions? Since you have been mentioned of automatic AM radio chip instead of space grade ones is not important at all. That's the reliable transmitting later. Curious about the talk. Yes. As I mentioned, one reason for our success is that this was our third CubeSat mission, and in the team I had students, actually one doctoral student. Actually, Antti Kestelä already gave a presentation 2 years ago, who involved in the whole, even in Aalto 1 and Aalto 2 CubeSats. So it means that we had in the team almost 10 years expertise on the CubeSats. So we knew possible problems, but I agree that the question about, for example, what chip we use, we had to use this kind of chip that we can control easily. We didn't know exactly what are the radiation tolerance of that chip. Some information to my recollection we had, but not very good knowledge. So it means that we didn't know will our radio instrument work in space, and if it works, how long it will work in space. And this is of course the problem. If we could have a lot of time and money, we could have made our own test. We could have put those to chip and our, let's say, radio instrument to plasma chamber and use high energy particles and look how our chip works there. But we didn't make any this kind of, or we could have used a high electromagnetic noise and look how our instrument works. But we didn't know it. So it was in that respect, also in that respect, we are very happy that the instrument is still working and it worked. But I agree, if you're using COTS, it's of course, it's one criteria is that use as good radio tolerant components as possible. But maybe one thing is that please remember that our altitude is only about 600 kilometers. We are below the radiation belts. So therefore, in that region, we don't have such a big risk if we would have, if we had to go through the radiation belts. I'm sure that our satellite and instrument would not have worked in such a high altitudes. So thank you for the question. I agree. This is a very, very critical, important issue.
Yeah, because you're at such a high altitude at 600 kilometers, so you could be there forever, without losing it for now. Okay, any other questions to Isa, Professor Kallio? It's a good opportunity. You can see that they spend time having free. And in fact, if you're interested, you should go back to our video corrections. You can see almost about 2 years ago, we have 2 talks from one from Isa and one from his student, and you can see how they how they kind of develop their program. Yeah, and until today they have this successful menu CubeSat, giving a lot of experience. Now, before you go, Isa, I want to know what will be the next step? You have any other? You must have other plan, right?
Yes, at Aalto University, we have new satellites coming. The next satellite, we don't exactly know what is the time, but probably by beginning sometimes of the next year, Aalto 3 CubeSat will be launched. So as I mentioned, Aalto 1 was the first one, Aalto 2 was the second project, and Aalto 3 is now the third project. And in addition to that one, there is one project called For Sale project. And this For Sale CubeSat project is more challenging because it will really go through the radiation belts. So and actually one of the motivation is really to test radiation dose with the CubeSat, and also how CubeSat can survive in this kind of high altitudes, where, as I said, for example, our satellites would never have survived because we didn't have any, let's say, aluminum protection of our components. But in this For Sale project, they really have over a kilogram, to my recollection, maybe over about 2 or 3 kilograms shielding, because they have to go through the radiation belts. So there is hopefully two satellites will be launched next year. CubeSats, yeah. Aalto 3 satellite is a 1 unit, so very small, but this For Sale 2, it is 6 unit. So because you need a lot of shielding.
And you have anything to do with any test with this idea of a e-cell technology?
Yes, this e-cell. So it is as I said, I worked 25 years, and Dr. Pekka Janhonen, he's a very, very clever physicist, and he had invented this kind of e-cell technology. And actually in For Sale that I mentioned, this For Sale 2, they will also test this kind of e-cell technology. So their goal is to inject or roll out a very long, I should remember, but I don't remember, several hundreds of meters of long wire, and include power, the potential to that power, and really look how you can affect the movement of the satellite. So in this For Sale 2 that is planned to launched hopefully next year, this will be tested.
And can you give a talk on that also?
I cannot give, but Pekka Janhonen, he can give it. I can give his email address.
Okay, I would like to invite him. Pekka, right? Is it Pekka? Pekka, yeah.
Pekka, yes.
Right. Okay, I would like to, love to have a talk on this very interesting idea.
Yes, I fully agree.
So that's one thing. You guys are doing this very well, and then the e-cell, and then also you have this ICE-I, right? From Finland.
That's true. So maybe just the background. So ICE-I was a spin-off from this first Aalto University CubeSat, Aalto 1 CubeSat project. So those students who involved in Aalto 1, they make this company, and now it's a very, very world famous, to my knowledge, is the most accurate SAR constellation in this size in the world. To my recollection, they have launched over 20 satellites, and more. There are more to come. And so it's a synthetic aperture radar, so you can see through the cloud, and of course also make observations on the night side. So it gives more possibilities than optical cameras.
And do you know, you must know people there, right? Do you think you could also help me to invite one person to give a talk on the ice?
Yes, I can send you the names if you want, or I can also ask by myself.
Okay, why don't you ask him? You know, it's better than I write to him. Yeah.
Okay, yes, I will take contact
Yeah.
to my contact points and ask
If
if they,
he said yes, then I will write to him.
yeah, thank you. Yeah, yes, I will do that one.
Yeah.
I will
Okay.
check.
Isa, so much. Thank you so much. I will talk to you some other time about this pipe dream things, right? I would write to you about that too. Whatever
Thank you.
some other time.
Thank
Okay.
you.
Thank you so much, Isa, and everybody for coming in. You know, I think it's a very enjoyable talk and learn a lot, and then knowing that yeah, by listening to them, we learn quite a bit, you know, how to run the business. Yeah, thank you, Isa. I talk to you again next time.
Thank you very much for invitation. It was a pleasure, and have a nice day. Have a nice evening, I think so.
Yeah, but next time, please make sure that your camera is working, that so we can see you.
Yes, I really apologize. I did. Okay, yes, I will do that. I will certainly I will do that.
Okay. Okay. Bye bye.
Thank you. Bye bye.